Hey, I'm Mel Strong, and this lecture is on convective weather and convective storms. And it follows the previous lecture I gave, which was on convection in the atmosphere. So watch the introductory lecture to convection in the atmosphere first, and then come back and watch this, and it'll make more sense. But what we've said so far is that when you look out and you see a bunch of little puffy clouds, what we now know is that underneath each one of these is a rising plume of air. And the reason the air would want to rise is because if I look out here, I see a variety of vegetation, variety of textures, a variety of terrain. And so the temperatures out here are not all the same. So places where it's warmer will want to rise preferentially. And so you get these plumes of rising warm air that we call thermals. As they rise, they expand. As they expand, they cool. And eventually that air is cooled down to its dew point. And when that happens, you get a saturation of the air, and the relative humidity is 100%. From that point forward, you have a cloud, and whether or not the air continues to rise just depends on whether or not it's still warmer than the air around it. So this lecture basically focuses on the question of what happens if this cloud continues to grow. But first, let's talk about some sources of heat. So down here, the sources of heat are just simply the sun. But what you could have is you could have something like maybe a fire. So we have a source of heat here, and you can see the smoke, but then right here something happens. And above this point, you've got a cumulus cloud. And this cumulus cloud is a mixture now of cloud and smoke. This rising warm air expands and cools, hits the dew point right here, and you get a saturation. So this is called a pyrocumulus cloud. It's a cumulus cloud that forms over a fire. Now it may seem weird that you can condense water out of smoke, but remember, the air already had some water vapor in it, and then a fire actually adds water to the air. Whenever you burn fuel, whenever you burn hydrocarbons, we talked about this in the previous lecture, it adds water vapor to the air. So it's pretty common that you get cumulus clouds forming over fires. Here's another one. You can see exactly the point where temperature must equal dew point. Right there we go from all smoke below to smoke and a whiter cloud above. This is a kind of lousy video, but it's a time lapse of a wildfire, and it's showing that you can see rising plumes of smoke and warm air. And you can see the point where the air cools until it hits the dew point. The temperature hits the dew point, and we get saturation and we get clouds. So you can see the white is the pyrocumulus clouds forming over the hot fire. You can also get them over volcanoes. So you've got a source of heat down here. This black material is what we call ash, and ash are tiny little fragments of rock and glass that are coming out of the volcano. But right there, you notice it changes, and you got this puffiness. So this is ash plus cloud, and so as the air is rising, it's cooling, and eventually the temperature equals the dew point, and you get a cloud that's also growing in with the ash coming out of the volcano. Sometimes, as humans, we create clouds, and so this is an example of one such case. Think about all of the things that we have blacktopped. So big parking lots, airports, we pave over large areas with dark material, and it gets really hot. So this is an example of an Air Force base in Florida. So every day the sun comes up, warms up the blacktop, and that warm air starts to rise. It then condenses, forms a cloud, and that cloud sits over the Air Force base, but the wind blows it off to the side. So you get this kind of elongate cloud that goes off into the distance. So this is what it looks like. So we're standing at the Air Force Base. There's that cloud, and you can see the wind's blowing it off into the distance. So they basically have this cloud that just sits there all day long, day after day after day. Another source of heat are mountains. And so to illustrate this, imagine that we don't have a mountain first, and we've got a flat terrain. And as I go up in the atmosphere, I would notice that the temperature gets cooler and cooler and cooler and cooler with height. Okay, that's what you'd expect. But now let's imagine that we stick a mountain in this. Okay, so when the sun comes out and warms the earth, We'll talk more about this in a future lecture, but for the most part, sunlight just travels right through the atmosphere and doesn't affect it. When it impacts the surface of things, it will warm them up. So here you have this surface sitting up in the air. So right here where the temperature up there is 40 degrees, right here, maybe when the sun comes up, it warms it to 50, right? And up here where the temperature is 30, maybe the sun hits it and warms it to 40. So the point is you've got this thing that's up in the atmosphere that's warmer than the atmosphere around it. So what will happen is air will start to rise above the mountain. And if it rises enough, then we start to get condensation and a cloud will form above the mountain. So this is what happens around here a lot. So if you live in Albuquerque, a lot of times you'll notice in the summer that we'll get cumuliform clouds that start over the sandias. And in fact, this is what it would look like if you were to climb to the top of a mountain and look up during when this is happening. So right here where I'm standing looking straight up, there is warm air rising above our heads, going straight up and then hitting the dew point and turning into a cumulus cloud. So this is what the bottom of a cumulus cloud looks like, right where the warm air rises off the surface. And so this cloud just kind of sits here for hours growing. You can see there's movement in here, but the cloud pretty much stays in one spot. Here's another view of it. So what we've been saying so far is that thermals, you can't see thermals, right, when the warm air rises from the surface. But this one, the warm air is rising right in front of us. And so right here, you should be able to make out that the warm air is rising right there and going into that cloud. So right there, temperature equals dew point, and you're getting 100% relative humidity, saturation, and a cloud. So when you look from space, you can actually see this effect really clearly. And I've got a satellite image here. I'm at a website called Worldview from NASA. And right now I'm looking down over here over New Mexico. You can go to this site if you want. If you do, the date down here will be the current date, and you can change it to, so I'm looking at July 18, 2017. Just happened to be a day where this happens, but this is pretty common what I'm going to show here. And what you see is you see that there are clouds in certain areas and then not others, right? So these areas that are kind of darker green are higher elevation. They're higher elevation, they get more precipitation and therefore have more vegetation. We'll talk later on about why they have more precipitation on mountains, but they do. So for example, here we got mountains, we got a valley, we got mountains, and you can see that the clouds are preferentially forming over the mountains. In fact, we can go down here, and that gray blob right there is Albuquerque. Okay, so there's the Sandias, and you can see there's clouds over the Sandias. If we go a little bit to the north, as a side here, do you see this thing? So this fuzziness are ice crystals coming off of a cumulonimbus cloud. So that's the anvil as seen from above. So this is the cumulonimbus. This is the anvil that's spreading out with all the ice in it. In fact, if I go back down here, so again, back down to Albuquerque, this one right here is another one. You can see with the fuzziness of it. And a lot of times what will happen is that the cumulonimbus will form over the Sandias and then move on and continue to drift across the city. This time of day, by the shadows, I would estimate it's probably late morning. And so what we notice a lot of times in the summer is that the first clouds you'll see are over the mountains. And then once they grow, sometimes they'll drift off and go somewhere else. But they typically start over the mountains. A related idea is what happens when you have land surrounded by water. So this is the peninsula, this is Florida right here, and so you got water on both sides of the peninsula, and you can see how many more clouds are actually over the peninsula than the water. So we'll talk about this in a future lecture, but the ocean doesn't change its temperature much day to day, and so the temperature in the water here is pretty consistent day and night, whereas the temperatures on the land vary quite a bit more between day and night. So during the day, the land heats up more than the water, and you get rising air, and you get a whole bunch of cumuliform clouds out of this. So one of the things that we are going to get into here is try to figure out what happens when a convection cell grows to different heights. And we have some terms to describe how high they grow. So it's going to seem backwards, but in weather, when we talk about how high a convection cell grows, we call that its depth. Okay? So if I have shallow convection, that means the convective cells are not going very high. If I have deep convection, that means the cells are going much higher up into the atmosphere. So shallow convection are days where we might have no clouds at all. The thermals don't even get high enough to even make a cloud, or you get small cumulus clouds. Deep convection, you get these really tall towering cumulus, or maybe even cumulonimbus. So we're going to show you some examples here. So these are some cumulus that are growing. So we're over the Sandias. We get plumes of warm air rising off the mountain. But you'll notice that these cumulus don't really grow very high, right? They're kind of staying about this height. And you watch them, they'll grow, and they'll die, but they never get much taller than this. Okay, so that's pretty shallow convection. So the thermals are rising from the surface, and then they get about that high, and then they sink back down. Here's another example. So a lot more convection happening in terms of plumes of warm air rising, but you'll notice that all these things aren't very tall. There's a limit as to how tall each one of these cumulus clouds are. If you watch this for a while, you'll see some of them, like that one's going to die there, and then another one's going to form. So they're forming and dying all the time as these thermals rise, hit the dew point, and then cool back down. Now, what if we are able to convect a little bit more? And so this is what's happening here. So we might call this moderate convection. We've got a thermal right here. You can see that this is right where the warm air is rising up from the mountain, going to the bottom of the cloud. And now the conditions are a little different, and this cloud is able to grow vertically. And it's growing a lot more than it did in the previous movies. So we might say, yeah, this is moderate convection. It's growing. These convection cells are definitely growing more than they did earlier. Here's another pretty significant convection cell. We might even go as far as to call this deep convection here. So that here the mountain, again, is warm in the daytime, sending up a plume of warm air and forming this big convective cell right above it. So the question is then, why is it that some days I get convection that's deep and sometimes it's shallow? So there's several reasons, but one of them is just simply how hot is the air down here where it rises. So some of the earlier movies I showed you, the convective cells were very shallow. It was early in the morning. They weren't very warm yet. Now this one is later in the afternoon, and you can see that they're starting to grow taller and taller. So you can see this one now. Notice that fuzz there. So at some point, and we'll see it again here, at some point, there's some fuzz right there, these convective cells will grow tall enough that they're going to be forming ice crystals. And if you might remember from the cloud lecture that ice looks fuzzy, right? So you can see how this one's starting to kind of make an anvil shape a little bit, but it's a different texture. Like there's some fuzz right there. So there's some ice, okay? So these clouds are a mixture. They're a mixture of ice and liquid. The hard, definite boundaries, that's liquid. Where it starts to get more kind of fuzzy on the edges, that's ice. Okay, and this is important for what we're going to be talking about next. But in order to make precipitation, in order to turn a cumulus into a cumulonimbus, we have to make ice. So here's another example. And again, you can see the sharp, definite boundaries here. That is liquid. But up here, you're starting to see that fuzz right there? It's a little fuzzy on the edges. This is starting to make ice. Okay, and the ice is going to be starting to form near the top of the cloud. So one more movie here of convection. And so here, see the fuzz right through there, a little bit. Okay, so as this thing convects, you'll see areas that will start to turn a little bit fuzzy. Like here's some over here, a little bit there, some right there. That's ice. Okay. So at the top of a really tall convecting cell, you will form ice. Now that ice is going to be really important here, because what's going to happen is that ice is what's ultimately going to be responsible for nucleating precipitation. So this is an image that we saw in the previous lecture. And we were talking about how the cloud droplets are actually microscopic. And raindrops themselves are, several millimeters across. And so the question is, well, then how do we go from little tiny microscopic drops to these relatively giant raindrops? So most people have the impression that cloud droplets will just grow and grow and grow until they're so big they become rain and they fall out. And it turns out that actually does not happen. It can happen in a few places with really, really high dew points, like in the tropics. But where we live, that pretty much does not happen. There's a different process at work that's going to get us from these little tiny microscopic drops to big raindrops that are big enough that you can, hold in your hand. So let's imagine that we've got one of these really tall cumulus clouds. It's got some fuzz on top. That's our ice. And the ice itself would be little tiny microscopic particles, little tiny crystals floating in the air. And they're going to drift their way down into the rest of the cloud. And before we talk about what happens next, we'll talk a little bit about how weird water behaves in the cloud. Because down here on the surface, we're used to the idea that water freezes at 32 degrees Fahrenheit or 0 degrees centigrade. So if I have a bowl of water and it's sitting out at 32, I know that eventually it'll completely freeze. But the weird thing is that if you have really, really, really tiny microscopic droplets of water, which is what we have in clouds, because remember, cloud droplets are microscopic. When they're this tiny, they have very little surface area. It turns out that liquid water can stay in the liquid state below the freezing point. In fact, it can stay liquid all the way down to minus 40 degrees Fahrenheit, which happens to also be minus 40 degrees centigrade. So these little droplets out in the cloud, even though the temperature is below freezing, they stay in their liquid form, and that's called supercooled water. Okay, so in our cloud, there's actually 3 zones. At the top, we have all ice, and the top part of the cloud is going to be usually less than minus 40 degrees Fahrenheit or so. Below that, we have what's called the mixed portion of the cloud. It's ice and supercooled water. Okay, and by water I mean liquid, right? And so then below that, it gets warmer as you go down. We get to the part that's all liquid. And this part is going to be above 32, right? This is called the warm part of the cloud. Okay, so if you were to watch what was happening up here in this ice, what you would notice is that as the ice, these little tiny microscopic ice crystals, when they drift down into the supercooled part of the cloud, you would notice that those ice crystals start to grow and they get bigger. And what's happening here is another unusual process that we don't experience in everyday life. And what happens is, if you were to take ice crystals and put them in the presence of supercooled water, so this represents the cloud droplet, and this represents the little tiny microscopic ice crystal that floated in from above, that water molecules will preferentially attach themselves to the ice. In other words, they'll actually abandon ship. They'll leave the supercooled liquid, the little cloud droplet, and they'll attach themselves to the ice. So what happens is the ice crystals start to grow and get bigger as the cloud droplets become smaller. So in our cloud, what happens is this area is called the Bergeron process. That's the name for this. And the Bergeron process produces, and I'm making these way larger than they would be with scale to the rest of the cloud, but eventually you get to something that you might recognize, because at some point you make something that looks like a snowflake. And so these snowflakes fall, and if you were up in this part of the cloud, you'd think, oh, it's snowing. And the snow falls and it heads towards the warmest part of the cloud. And when it passes through to the warmest part of the cloud, the snowflakes melt. And then each one of those snowflakes melts to become a raindrop. And by the way, I'm drawing raindrops in a very incorrect manner, but every time you see rain drawn in a cartoon, they're always drawn like little teardrops, but that's not true at all. Raindrops are actually perfectly spherical when they fall through the atmosphere, but when they hit your window, they turn into a teardrop shape, so that's why everybody does that. So I'm propagating some misinformation here. But anyway, these then fall out of the cloud as precipitation. And at this point, once you have precipitation falling out of the bottom of the cloud, then you have a cumulonimbus. So we can watch this process. And so let's pay attention to this one right here. So that's a cumulus cloud right now. Not really any ice to speak of. It's got a flat bottom. There's air that's rising up as thermals, hitting the dew point, relative humidity 100%, all that good stuff, going up into the cloud. And the cloud is growing and getting taller. So this material up there, see that's starting to look like some ice up there. Okay, we're getting little bits of ice. Keep watching it here. There's a little bit of fuzz there. Okay, now over here, that's definitely starting to look like ice. It's getting a fuzzy edge on it. And then down here, if you watch, right there, we're starting to see precipitation. Okay, so we got ice for sure right there. We got precipitation coming out of the bottom of the cloud there. So now we've got cumulonimbus. Now sometimes what falls out of the cloud could still be snow, and the snow will melt on its way down, or sometimes it melts within the cloud. But the point is that every raindrop is a melted snowflake. So if it is raining down here, it's snowing up there. Now, if you lived in the tropics, it turns out that this process isn't required, and there is so much water vapor in the atmosphere in the tropics. The mixing ratios or the dew points are so high that actually you can get direct condensation of cloud droplets into bigger droplets that then fall as rain. And so this is a diagram from a textbook where it shows these coalescing cloud droplets that become a bigger raindrop, and as it falls down, it crashes into more of them, and it'll break apart into further ones. And they will come out of the bottom of the cloud, and no ice is necessary. But where we live, and pretty much anywhere in North America, we need the Bergeron process to make rain. Okay, so that's pretty much always happening in our part of the world. Now, another thing that happens is we've been talking about, up till now, we've been talking about how the clouds have air moving up into them, right? We did the whole convection activity. What's still happening with this? So there's warm air that's rising and entering the cloud and going up into the cloud. And it forms this upgoing draft that's called the updraft. And in fact, this part of the cloud right here, where the air is going in, is sometimes called the intake. So there's actively air moving into the cloud. Now, the other thing that's happening is we've got precipitation that's being formed on this side. So you've got another draft that's going in the opposite direction. So you've got air that's moving downwards. And this downward moving current is called the downdraft. And the downdraft comes out the bottom of the cloud with the precipitation. So if I look at a typical thunderstorm here in Albuquerque, so there's the precipitation. So the downdraft is occurring right here. There would be some kind of wind, vertical wind coming down with that. The intake, the updraft, is happening somewhere over here. So somewhere over here is where the air is going up into the cloud. Now, what can happen is that these downdraft winds can pick up a lot of speed for reasons we'll discuss in a second. And as they pick up speed, they come down and they come crashing into the ground. And by picking up speed, I mean, we've actually measured some in excess of 70 miles an hour, comes straight down. And when they hit the ground, they splat. And so you can see how you've got rain coming straight down and then it's like it's squishing outwards. That is wind. And this kind of downdraft, where you have a really strong vertical wind associated with it, it's called a microburst. So anybody that's down there right now is not only getting rain, but it's getting a strong wind associated with it. So here's an illustration of how that would look. So remember that up in the cloud, the relative humidity is 100%. So there's no evaporation taking place. As soon as raindrops leave the cloud and go into the air column below the cloud, they're entering an environment where the relative humidity is less than 100%. Because that happens, the raindrops are subject to evaporation. If you live in a dry climate like we do, you might have really low relative humidities down here. And what that means is you get evaporation of the raindrops as they're falling. If raindrops evaporate, remember from several lectures ago, that removes latent heat from the system. So you have to imagine water molecules leaving with their little boxes of thermal energy in this diagram. That means this air column that's now raindrops and air, and the whole thing's being cooled by the removal of latent heat. This whole column here is becoming colder, and when you make air colder, it becomes denser. And when it becomes denser, it sinks faster. So this whole blob becomes a sinking blob of cold air that's accelerating towards the surface of the Earth. And it hits, again, like I said, it can hit 70 miles an hour, has nowhere to go except out. And so it produces these winds that move out in all directions. Those are called the outflow. So back in our diagram here, we can add this in. So if this is happening in our cloud, where it hits the ground and spreads out, this cold air has a name. It's called the outflow. And right at the boundary where this occurs, this is called the gust front. And we'll talk more about that in a second. But right now, the way that we've drawn this area right in here is where the microburst is occurring, right? So if you live right here during this, you're getting a lot of rain and a lot of wind as well. So here's an example of what we call a wet microburst. And you can tell it's a microburst because you can see it spreading out on the edges there. So there must be some pretty strong wind that's coming down, hitting the ground, and spreading out. So here's some video footage from a microburst occurring in Phoenix. And you can see that this is the column, this is the downdraft. You can even see it moving in this. And it hits the ground and spreads out. So people that are living down there are experiencing not only high amounts of rain, but high winds as well. Okay, and you can see it spreading out to the side there, right? So even people out here are experiencing the outflow, the wind that's coming from this severe thunderstorm. Here's another one from Tucson. And so this one, it's during the middle of this downpour, it's going to generate a microburst, and they're going to zoom in on it. And you can see it come down and splat against the surface down there. They'll show it a couple more times here. So here it is again. So there's a blob of cold air comes down, splat. And then again. So each time you see this, they're just showing the same thing over and over. But it's a particularly cold blob of air, accelerates on the way down, splats against the ground, creates a high wind that spreads out in all directions. So anybody down here is experiencing not only rain, but a sudden pretty strong cold wind. In fact, this is what it looks like from the ground in one of these. And we're somewhere in Arizona. And we're under a thunderstorm, but the microburst hasn't started yet. There it is. And we can get hurricane force winds. They don't last long, but enough to do a lot of damage. They'll knock over trees and houses and cars and all kinds of stuff. Now, there's another type of microburst. What we just saw was something called the wet microburst because it's raining at the surface. Everybody gets wet. There's also something called a dry microburst, and we are particularly prone to these in New Mexico and Arizona. So what we're looking at here is we got some kind of cumulonimbus up off the screen here, and these streaks, that's rain that's coming down, and it's evaporating on the way to the surface. Well, as it's evaporating, as we just said, you're losing latent heat. So you're making this column of air cold. And we call this virga. So virga is whenever you have rain that just disappears on the way to the ground. So here it is again. So here's rain that's falling as liquid, but the air column down here is pretty dry, low relative humidity. You get evaporation, 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 and then finally there's nothing left. You're standing down here, you're not getting rained on, even though the rain's falling above your head. But what is happening is the evaporation of all that rain is removing latent heat, and you're making a column of really cold air that's really dense, and it sinks down and goes splat against the surface. It just doesn't have any water with it. We call that the dry microburst. So here's one. So we can't see the cumulonimbus that's up off the screen here, but there's a blob of invisible cold air that has sunk down, hit the ground, and you can see it spreading out. So if you're down here, the experience is all of a sudden it got really windy, and the air suddenly got colder, usually. Here's another one, and it looks like, does it look to you like somebody just dropped something out of the cloud and went down and went splat? That's pretty much what happened. There was some rain that came out, it completely evaporated, made a blob of sinking cold air, accelerates, runs to the ground. That's all dust down there. That's all dust from the winds from the dry microburst. Now, microbursts can be pretty dangerous. And if I go back to this picture that we just drew, so it's dangerous to be down here in the microburst, but this outflow is going to keep going. In the front of this gust front here, I mean, it can still be moving along pretty good clip, maybe 70 miles an hour or something like that, and it can do a lot of damage. So a few years ago at Indiana State Fair, they're setting up for a concert, and there's a thunderstorm that's coming, and you can see it in the distance there. And the thunderstorm produces a microburst, which makes the outflow. The outflow wind comes and basically invades the fair and knocks over this whole stadium setup and killed, I think, 7 people and injured about 50 or so. So that is the outflow that did that. Another thing that can happen is if you live in a place that's very, very dry, like where we live, as this outflow is going across the surface, not only is it doing damage just from the wind, but it can be blowing up a big cloud of dust, and you essentially make a big dust storm. And that's called a haboob. It's an Arabic term from the Middle East. They get a lot of those over there. Here's a picture of one, and there are some famous images in movies of haboobs from the Phoenix area. And so we got a cumulonimbus here, and it's generating an outflow. So this whole thing is a big blob of cold air creeping along the surface, and as it moves across the surface, everybody that's in its way gets covered in dust. So there's another picture of it from above. So here's a good time lapse of a haboob. Again, this one's from Phoenix area. Here it comes. Notice also that there's clouds right above it that grow along with it. And that's because as the cold air comes along the ground, it shoves up the other air out of the way and actually will form clouds above it and sometimes will trigger new thunderstorms. Here's another one. Here's some excerpts from, again, another YouTube clip where this guy drives into the haboob. So here you can see the edge of it. So that would be the gust front right along the edge. And he's going to drive right into it, because why not? And as he does so, you'll see that at its peak, it pretty much looks like night. And later on in the semester, we'll talk about droughts. And if you've heard about the Dust Bowl drought in the 1930s, they were dealing with this kind of on a regular basis in places like Oklahoma. So this is the middle of the day, and it's starting to look like the middle of the night. So this might explain something that you've experienced yourself if you live in New Mexico. You'll be at home, and it'll be a nice clear day, no clouds, no wind completely calm. And all of a sudden, out of nowhere, you suddenly are hit by this blast of wind. Like, where did that come from? Well, it could have been an outflow. So what might be happening is clear on the other side of the state, like maybe in Carlsbad, they've got a severe thunderstorm, and they get a strong downdraft, which then turns into a strong outflow. And believe it or not, the outflows can go all the way across the state, and you can track them on radar. I've tracked them on radar all the way from eastern New Mexico clear into Arizona. And so it's so far away that you actually don't even see any clouds, right? I mean, the cumulonimbus itself is clear out of sight. So that's something that we actually experience here, especially in June and then into the monsoon season. You may experience these outflows that just come out of nowhere. So another one of the hazards of convective storms is that of hail. And scientists are still trying to work out exactly how hail forms, but it seems pretty apparent that hail must have to spend longer in the cumulonimbus cloud than standard rain. And one of the clues is that often hail has these growth rings. So if you cut a chunk of hail open, especially a large one, you'll see these concentric rings. And if you think about what we've talked about so far with these convective storms, so the story is, we create a snowflake, the snowflake falls and melts, and one snowflake makes one raindrop, which comes out the bottom. But we also have these pretty strong downdrafts and updrafts, and they're right next to each other in the cloud. So it's been speculated that what happens if some of these raindrops somehow got caught up in this updraft, and they got brought back up to the top into the frozen part of the cloud, and then they came back down. And as they did so, they would grow another growth ring. And maybe if the conditions were right, they could go around and around several times. So that's one idea. Now, some of the most recent research shows that actually that's probably not what happens. Probably what happens is that the initial raindrop falls down and then gets picked up and probably spins several kind of paths back and forth up in this supercooled part of the cloud before falling back down. So it's not necessarily a loop-de-loop as much as it is updrafts, just kind of giving it a little push now and then to keep it in the cloud for a little bit longer. So locally, we have a pretty famous hailstorm that occurred in Socorro 2004. And these are some pictures from that storm. As you can see, there are some, baseball-sized hail that came down during the storm. Storm lasted something like 45 minutes. And these are some pictures from people's backyards where the hailstones just smashed everybody's lawn furniture. And New Mexico Tech was in session, so the students come out to find their cars all beat up like this one or something like that. And occasionally, even today, you'll see a banged up car in Socorro with a bumper sticker saying, "I survived the hailstorm." I also posted a document on Learn that was kind of goes over some of the damage and some of the results from the Socorro hailstorm. Here's some pictures where all the back windows are broken out. These are cars at New Mexico Tech again. This is when this picture was taken, it was the largest ever measured hailstone. I'm not sure if it still is or not, but this is from Oklahoma. And if you look at this, it kind of looks like you see a bunch of individual hailstones that are all kind of stuck together like a conglomerate here. And the biggest hailstones don't come from New Mexico. They do tend to come from the Midwest. And we'll talk a little bit here exactly what's going on with that. Sometimes you can see the hail come down as it's kind of bright white. It's called the hail shaft. And it looks significantly whiter than normal precipitation does. Of course, one of the most dangerous hazards of convective storms is that of lightning. And lightning, it turns out, is not very well understood. It's very difficult to study because it can kill you. So there's a few things that we know. And it's been observed that in a lot of thunderstorms, cumulonimbus clouds, that there's an excess of electrons in the bottom part of the cloud and a deficiency of electrons in the top part of the cloud. So if you have excess electrons, that means you have a negative charge down here. You don't have enough electrons, you have a positive charge up there. Now, what would cause this? So if you've ever taken a balloon and you rub it on your hair and it sticks to the wall, so what you've done there is the motion of you rubbing it on your hair moves electrons from one spot to another spot, and then it gets a static charge. So remember that in the cumulonimbus, right, we've got the updraft, we've got the downdraft, and they're right next to each other. So it's very likely you've got places in the cloud where you've got air sliding past each other, and maybe that's stripping off electrons from one part of the cloud and bringing them to another. Maybe probably a more realistic possibility is that if you have solid particles like ice crystals and they bang into each other, that also strips electrons off. So it might be either one or some of both that do this, but in a typical cloud, you've got these electrons near the bottom and you've got a deficiency near the top, and these electrons, what they want is they want to get up to here. That's where they'd like to be. Well, it also turns out that you've got positive charges down here on the ground. So the Earth itself has a slight positive charge, especially compared to the bottom of this cloud. Well, when the charge builds up to a certain point, the electrons start coming out of the cloud in what's called a stepped leader. So this is not lightning yet. It's some ionized gas that comes out of the cloud, and these electrons don't know where they're going. So it's just kind of a random pattern, and they branch. And as they get closer to the ground, the positive charges that are down here, opposite charges attract. So they're attracted to this. So they're going to start climbing tall things, and they're going to make a little branch up into the air. Okay? So these guys don't know where these guys are. These guys don't know where those guys are, but they can sense each other, and that there's a mutual attraction between the positive and the negative charges. Well, eventually, one of these stepped leaders, which again is just randomly moving, it doesn't know where it's going, will accidentally come in contact with one of these, and these are called streamers, the positive charges from the below. So the stepped leader accidentally hits a streamer, and now you've got a connection between the excess of electrons down here and a deficiency of electrons down there, and the result is this is actually the lightning strike that you see. So all this stepped leader business that I just drew, that all happens within milliseconds, and you don't see it. What you see is when these two things touch each other and completes the circuit, and you get lightning, you get a current, and the current actually flows from ground to cloud. So if you slow down lightning, what you'll see is you will see the lightning discharged going up into the cloud. And that's the part you see. Even though it's a fraction of a second, that's what you see, and everything that came before that is invisible to the eye. Now I've got some video here that has been slowed down a lot, and we can kind of see these stepped leaders a little bit. So here's the first one. Now what you'll see, here come the stepped leaders out of the cloud. Now the ground's down here. That one did not hit the ground. You can see they're just kind of randomly shooting out. They don't know where they're going. This is not lightning yet. That one came close. And all of a sudden, right there, one of them hit the ground. Okay, and that's the actual lightning that you see. Okay, so I've got another one here. Again, slow down a lot. Here come the stepped leaders. You can see them coming down. And then bang, those two hit the ground about the same time, and then you get a return current, and that's the lightning bolt that you actually see. Now, watch these two buildings. Those two things, those are the streamers. Streamers are very difficult to photograph, so we have just a few images of them. Right there. I think there's one more here. Right there. Okay, so So if you go on YouTube, you can find videos of the stepped leaders coming down. It's very difficult to find footage of the streamers going up. They're a lot harder to photograph, but we have a few. Now, the other thing that could happen, besides these electrons coming down and hitting the ground, is they could also, in fact, get up here and join the rest of the cloud up there, right? Because they just want to get to a positive charge. Doesn't matter which way they do it. So you could also have, if the charge builds up, you could also have a connection between these two parts of the cloud, and you get lightning in the cloud, or you can get lightning from cloud to cloud. And in fact, when people have flown planes, intentionally flown planes through thunderstorms to study this kind of stuff, what they often find is that in a typical thunderstorm, that you might have a pocket, a positive charge in one spot, and then you'll have a pocket of negative charge in another spot. And you can have several pockets in different places, and you'll get charging from, discharging, I should say, from one to the other, where you'll get lightning will flash from one part of the cloud to the other part of the cloud, or from one part of the cloud, from one cloud to another cloud. So you might get lightning from here to here, you might get lightning from here to here. So not all lightning is to the ground. You can get what's called intercloud and intracloud lightning. So if you ever go on YouTube, there's a user named Pecos Hank, and he takes just fabulous lightning movies, and I mean he has like hundreds of these videos. So this is all intercloud and intracloud lightning, and you can see there's very little lightning actually going to the ground. It's going, from cloud to cloud or within one part of the cloud to another. But all lightning is the same thing. It's electrons want to get from one place to another, and when the charge builds up high enough, they can finally break down the air and make their own path, and that's what creates the lightning bolt. So associated with lightning is thunder. And the lightning bolt itself is about 6 to 8 inches wide. And so that during that brief instant when electricity is flowing through the lightning bolt, you've got this 6 to 8 inch air column that's being heated to thousands of degrees. And when you heat air, air expands. So what that means is, as the lightning is happening, the air in that column is being pushed out because it's so hot. But then, when the lightning's over with, there's nothing to keep that air column hot. And so the lightning's over with, there's very little air in here, and it's like a vacuum. And the surrounding air slaps that column back together, and that's what makes thunder. So every time you have lightning, it's generating thunder. Now, thunder moves at the speed of sound, and the speed of sound is it can go about 1 mile every 5 seconds. So when you see a flash in the distance, if you start counting 1 Mississippi, 2 Mississippi, 3 Mississippi, then when you hear the thunder, you will know how many miles away that lightning is, right? So if you count to 15 seconds, then it's about 3 miles away. Now, a kind of a weird thing happens if you're over 20 or so miles away. It kind of depends on the conditions, but it turns out sound waves, when they travel long distances, they refract upwards. And if you're over 20 miles from a lightning storm, you won't actually hear the thunder. It's actually moved up and refracted over your head. And I get this question sometimes from students asking me about heat lightning, and this is kind of a folklore that there's a certain kind of lightning that you can't hear, but that's not true. All lightning makes thunder, but if you're too far away from it, you just don't hear it. So you see flashes in the distance, but you never hear the thunder. So we've been talking about all kinds of hazards associated with the downdraft, right? We talked about the outflow and the Haboob and all that stuff. There's also some hazards associated with the updraft. And one of them is quite simple, which is that if you are in an ultralight aircraft or a balloon or a parachuter, you don't want to get too close to this cloud because you could literally get sucked up into the cloud. And there's an aviation term for this. It's called cloud suck. And so cloud suck is a real thing. And occasionally people get sucked up into the clouds when they don't want to be. Kind of a famous accident in 1925. This is a blimp, the Shenandoah, and it got too close to one of these convecting clouds, got sucked up in it, and crashed. And if you pay attention to the news, every once in a while you will run across people who have been sucked up into clouds during hang gliding or paragliding. Almost always they die. This woman somehow or another lived, and apparently she got sucked up into a cloud, immediately went unconscious, spent like an hour in this cloud, was covered in ice, and somehow or another survived all this, but most people do not. Of course, the most common hazard of the intake or the updraft is the tornado. And if conditions are right and you have really strong convection, the intake, the updraft, actually can start forming a tornado. And I just love this video because this guy, he's actually driving towards the tornado. And this is one of the cleanest views I've ever seen of a tornado. It's so much so that it kind of looks fake, right? Like if you saw that in a movie, you'd think, nah, that's fake. So in order to get a tornado, you need some very vigorous convection. You need very unstable air, but you also need a couple other things. One thing you need is something called wind shear. And wind shear means that the wind is blowing stronger above your head than it is near the surface. And what that does is it makes the air near the ground kind of spin in a circle, right? Then you've got thermals. So what we talked about, except the thermals now are going to push that spinning air upwards. And if it does it just right, you can take that spinning air and reorient it vertically. And then the air intake, the updraft, is spinning, and you get a tornado. Now, if you look at tornadoes across the country, there's definitely a spot that is where they're far more common. We call this Tornado Alley, and it's kind of centered here in Oklahoma. And so we're going to talk a little bit about why this is. Before I do, notice that the tornadoes, looks like in this map they completely stop right there. That's not entirely true. Here's another way that you can look at tornadoes. So this is 56 years of tornado tracks, every one of these blue lines. And again, like most of them are out here. And something is causing them to stop right around here, but they don't completely go away. And you can see there's little blue lines all over the place here where there have been tornadoes. So imagine if we just cut the country right in half, right through here, right through Tornado Alley. And we kind of looked at it from the side. So we're going to make what's called a cross-section right through the country. And we got south to the right, north to the left. What kind of air is over here? In other words, if we went south of the country, where do we end up? We end up in the Gulf of Mexico, right? So what's the air from there like? Well, it's going to be very warm, and it's going to have very high dew points, right? So a lot of water in that air. Air from the north is coming down from Canada, and it's going to be very cold and very dry. Okay, so we got cold and dry coming from the north. So if these two air masses come together, there's going to be a place kind of in the middle where you have warm air on the bottom and you have cold air on top. Now, if you remember from the convection assignment, we had one page where you drew the clouds and they went up a certain height, and then you went to the next page and we had cold air aloft and the clouds grew up off the page. Well, that's kind of what's happening here. Because you've got warm air on the bottom and cold air on the top, it's very easy for this warm air to convect upwards, and you get really tall, big, strong cumulonimbus clouds. And where do these two meet? Typically they meet right around Oklahoma. So if I go back to this map, I can imagine I've got warm, humid air from the Gulf of Mexico coming from the south. I got cold, dry air coming from the north. They kind of meet up in here. So why doesn't it happen over here? Well, the Rocky Mountains form a barrier for us meaning us in New Mexico, for the most part. The edge of the mountains prevents the cold air from coming down. It kind of keeps it on the side of the mountains, and it keeps the warm, humid air also on this side of the mountain. So these mountains really kind of keep both of those pools of air away from us. And so we don't have much, we don't have a lot of really unstable air. And we don't have really severe thunderstorms in this part of the country compared to over here in Tornado Alley. So that's all we're going to talk about with convective storms. I'm going to leave you with some time lapse of some convective cells. And next time we're going to talk about wind and air pressure and how those two things are connected. Thanks, and I'll see you next time.